You know, this morning we heard VJ talk about we are going to hundreds of thousands of CPU. I think this is the reason why I wanted to address the issue of balanced computing, looking at parallel processing from the overall parallel system point of view. So let's see how this works. There we go. So for some of you who doesn't know Panasas, I'll take just a couple of slides so my marketing people won't scream at me for not talking about our product at all. And then I'll talk about the parallel I/O with using PNFS, the parallel NFS, the standard that is part of the 4.1, the NFS 4.1. And I'll share with you some of the results that we work with ISVs when they move from serial to parallel I/O. I'll share with you some of the performance gain that they see and to show you why it's worth the investment of moving from serial to parallel I/O. So a little bit about Panasas. We founded by Garth Gibson. If you look at the first rate paper, it was written by Patterson, Gibson, and Katz. Gibson on that paper is Garth. So Garth is our founder, and he did his PhD at Berkeley. Sorry for mentioning Berkeley here, Stanford. But you guys won the axe this year, so I guess it's okay. We're actually a local company in Sunnyvale. The technology that we provide to people are basically parallel file system and parallel storage, and as an appliance. When I said appliance, what I mean by that is, we deliver to you everything built in. You just plug into your switch and mount the file system, and you go. So we can install terabytes of systems in a matter of hours, not days. Everything is built in. So basically, what do? We build high performance, scalable storage using parallel file system. We start with a single, what we call a shelf, which is 60, 40, 60, or 60 terabytes, and we scale them up to hundreds of terabytes. And many of our customers actually have petabytes of storage. Our customer use us in simulations, energy, oil and gas, gene sequencing, genomics, even financial analytic. So those are the type of customers, and Stanford is one of our customers as well. One of the reasons Panasas exists is because of parallel computing, right? As we move away from using Cray computing, go to cluster computing, to parallel processing. I guess for this audience, I probably don't have to convince you that parallel computing is now the mainstream. But for some of my customers that need to be convinced, I use this what I call the colorblind chart. It's you got it from the top 500, but let me walk you through this chart so it's a little bit easier if you just focus on the last, say, 5 years. So you can see that in the last 5 years, in the top 500, you see that number of processors now, on average, 4,000 to 8,000 processors, and that's showing us that parallel computing is now mainstream. But we can't just look at parallel computers, look at CPUs alone, right? Because not everyone runs LinPack for the experiment. Everyone runs real simulation, real data, and you have to access data. You have to be able to feed those GPU and CPU that we all have. And that's why you have to look at parallel system. It's not just parallel CPU, parallel computing. What is a parallel system? Parallel system is all the components that you have within your workflow, whether it is hardware, file system that you have, storage, and applications. If you don't change your applications, you're going to get hit with Amdahl's law, which basically said you're going to run at the slower speed of the link that you have, right? So the good news is we all know that multi-core is now the norm. Great. We're all happy with that. We get a lot of performance with that. Parallel file system, from PNFS and Panasas has been around for 10 plus years, so we're happy with that. And you take a look at parallel programming, OpenMP, MPI. The first time I programmed on OpenMP was over 15 years ago. So it's now become what I would consider robust, with MPI. So all those are great. The things that hasn't happened well, and I give it half a check rather than a full check, is porting code from 0 to parallel I/O. Why doesn't it happen? Why is it so difficult? Because it's not easy. It takes work. A lot of people, a lot of universities, companies I talk to, some of them don't have source code, believe it or not. It was written 10 years ago. The person who wrote them, gone. Right? So it's hard to move that from serial to parallel I/O. So it takes work. That's why it takes a long time. The good news is the industry coming up with standard like PNFS. So allow us to port code, follow certain standard, and also don't have to feel that we are tied to a particular vendor. That's why standard is a good thing. And that's what PNFS is. So let me talk to you and share with you what PNFS is. You all heard of NFS, right? Network File System. Sun brought that like 1983, and we all use it. But PNFS is basically to address the parallel I/O. So we need a parallel file system. That's what PNFS is. And there are many vendors that participated in this endeavor. So the names are up there. The big companies like EMC and NetApp, IBM are all major contributor to the PNFS standard, as well as Panasas. Clearly, since we have a lot of involvement with parallel I/O, we want PNFS to be standard. So in order to understand PNFS, there are three key concepts that you should understand about PNFS. The first one is PNFS separate metadata from data. So when you separate metadata from data, you need to have a separate component that handle the metadata. So sometimes, if you're familiar with Lustre or GPFS, they have something called metadata server. And that's the component we separate it out, and it manages by the metadata server. The data itself is still on the storage, on the hard disk that we all have. So that's one thing that you need to bear in mind is metadata and data are separated. So the second concept is layout. A layout is basically how do you distribute the data. I'll drill down into each of these components so you have a better understanding of how each of them work. So the second one is the layout, which is like a map of how the data is put on the storage. And the third concept is the backend. What is the format of the backend data? The standard right now defines three kind of backends. They have object backends, block backends, and file backends. And I'll get into a little bit more detail with all this. But these are the three concepts that PNFS introduces. So take a look at the standard itself. The PNFS actually define the communication protocol between the metadata server and the clients. The clients are your compute nodes. You may have thousands of them, or hundreds of thousands or tens of thousands. So it define that protocol communication. How the clients and storage communicate is actually defined in other standards. We already have SCSI protocol and even NFS protocol that dictates how the clients and the storage communicate with each other. And how the metadata server and storage communicates is also already defined in other protocol as well, like iSCSI. Okay, so that the PNFS, all it does is define that protocol between the metadata server and the clients. The layout piece, the best way to understand the layout is imagine, say, you have 10 gigabytes of data. Let's say you have 10 gigabyte of file, 10 gigabyte file, and you chop it up into 10 pieces. Okay, when you chop it up into 10 pieces, so 10 gigabyte, let's say for easy of argument, I chop it up into 1 gigabyte piece. So you have 10 pieces. So where do these 10 pieces go? These 10 pieces are going to go into different location of storage that you have. It may go into this one, block number 35, go into this 35, block number 2. So this is a map, so you know where it is. So that's a layout. And that layout is kept by the metadata server, and it's handed out to the clients when you need it. The clients may manipulate and change the layout. But once the client does that, it will send it back to the metadata server. Metadata server can recall those maps and then say, okay, somebody has changed it. Now, the rest of you guys, here's a new map. So that's how the layout works by the metadata server. On the client side, because PNFS is a standard, it's part of Linux kernel. Okay, in the Linux kernel, it's actually we'll be able to communicate to different type of backend. And the reason we need different type of backends is because different vendors deliver storage using different methods. For the good example, EMC tend to stay with block-based. NetApp tends to stay with file-based system, and Panasas use object. So we have different backend. Thank you. We use different backend, and as far as user like us concerned, we don't actually have to know this detail. As long as we run Linux. So let me show you the roadmap of Linux. If we run Linux kernel, say 3, which is going to be in Red Hat 7, all these backends already built into the Linux kernel. So you actually just have to load the kernel, and the kernel will communicate with the metadata server. It will know that, oh, you have object, you have file, you have block, all of them. You actually can work with all of them. And that's what the wonderful thing about having standard, right? So the Linux kernel has all of these already. We actually submitted the new kernel to Linus last month that has the RAID 5 in the backend, and that's going to go in. That's already went in. Should be in the 3.2. If you follow Linux, Linus tend to release on Christmas. He likes to release a new kernel on Christmas Eve. So watch for that. We're going to watch for that, and hopefully the backend will contain the code that we submitted from last month. So on the server side, you have you can download this from the Git tree and build it yourself. And let me tell you, you got to be a little bit of a, I call black belt Linux expert to build all this kernel yourself. But if you want to play with it, you can. I actually have a better suggestion. If you want to play with it, you actually can use Panasas, because Panasas already built all this for you. It's already inside the Panasas product. Since this is not a product pitch, I'm not going to go into detail, but I want to let you know that because the way that Panasas is built in, or the metadata server and server, it's already built in for you. We have a concept called director blade, which is the metadata server and storage blade that has data, and it's all put into a shelf. And we found that a ratio of 1 metadata server per 10 storage tend to be a good ratio for us, depending on your workload, clearly. So I want to share with you some of the results that we work with ISV like ANSYS. They have a Fluent, we work with them on a Fluent code, and they move from using serial I/O to parallel I/O. And when they made that effort, they see over 2.5 times performance improvement, and they're pretty pleased with that. So we also work with another company called CD Adapco. What they do is another CFD package. They have a code called STAR-CCM. When they move to parallel I/O, they see over 3x performance improvement. As you increase the process count, when you have 16 processes or 16 nodes, when you have a serial I/O, when you increase number of processes, your performance doesn't actually go up because it's bottlenecked by the head node. When you go to parallel I/O, you can see the performance can go up. When you have low number of processors, you're limited by the amount of load, the number of clients that you can use. As you add that in, up in this example to a 64 processes, you get almost 800 megabytes per second. And when you add more processes, the performance drop. And that's because the number of spindles is now exhausted. So what you have to do, you want to get more performance, you have to add more spindles, right? So this is a write performance. This is a read results. It's basically follow the same trend. The only difference that you notice between the two is that the absolute performance is probably 2x. The reads is faster than writes. The reason for that is, write, you have to worry about coherency. You have to make sure that all the writes, you don't write over each other, whereas the read, you just read and continue to read in the streaming mode. So that's the result. I think I'm running out of time, so I'm going to give you a last example. And this is a seismic processing. We work with a company called Halliburton, which is a very large company, software package called PROMAX. It's a PROMAXISEISSPACE. It actually does the parallel I/O using an open source parallel I/O package called JavaSize. And you can actually download and play with this. We work with them, and just recently we helped tune the last JavaSize last month, and we're seeing performance, going up to almost 5 gigabytes per second using full shelf. And the peak performance on a full shelf is the 6 gigabyte per second system, and we're getting almost 5 gigabyte per second out of that. So that's 80% of peak. So that's pretty good. So I guess I'll close by saying that it's great that we all using thousands of processors, adding CPU, but it's very key that we make sure that all of our systems are parallelized as well, not just one component. You don't want to get bit with Amdahl's law. You don't want to have 10,000 of processors all running through a single head node to do I/O, right? Because that means your investment on the CPU that you put in are really wasted, because most of the time it's going to do is going to be waiting for the data to come in. So it is important that we look at parallel system, not just parallel computing. Thank you for your attention. I'll take any questions if you have any.